Welcome to this video, where we will explore the fascinating history of calculus, one of the most powerful and influential branches of mathematics. Calculus is the study of change, motion, and infinity, and it has applications in many fields of science, engineering, and economics. But how did calculus come to be? Who were the main contributors to its development? And what challenges did they face along the way? In this video, we will answer these questions and more, as we trace the origin of calculus from ancient times to the modern era. Let's begin. Calculus is the study of change, motion, and infinity. It allows us to calculate rates of change, such as speed, acceleration, and slope, as well as areas, volumes, and lengths of curves and surfaces. It also helps us to model natural phenomena, such as the motion of planets, the growth of populations, and the spread of diseases. There are two main branches of calculus: differential calculus and integral calculus. Differential calculus deals with the concept of derivatives, which measure how a function changes as its input changes. Integral calculus deals with the concept of integrals, which measure the total amount of something that accumulates over time or space. The fundamental theorem of calculus connects these two concepts by stating that a derivative of an integral is the original function, and the integral of the derivative is the difference between the values of the original function of 2 points. There are also other branches of calculus that extend or generalize these concepts, such as multivariable calculus, vector calculus, differential equations, complex analyses, functional analyses, and differential geometry. These branches deal with functions of more than one variable, functions that take or return vectors, equations that involve derivatives or integrals, functions that involve complex numbers, spaces of functions, and curves and surfaces in higher dimensions. These branches have applications in many advanced fields of mathematics, physics, engineering, and computer science. What is the fundamental theorem of calculus? The fundamental theorem of calculus is a theorem that links the concept of differentiating a function, calculating its slopes, or rate of change at each time, with the concept of integrating a function, calculating the area under its graph, or the cumulative effect of small contributions. The theorem has two parts. The first part states that for a function f, an antiderivative or indefinite integral f may be obtained as the integral of f over an interval with a variable upper bound. This implies the existence of antiderivatives for continuous functions 1. The second part states that the integral of a function f over a fixed interval is equal to the change of any antiderivative f between the ends of the interval. This greatly simplifies the calculation of a definite integral provided an antiderivative can be found by symbolic integration, thus avoiding numerical integration 1. The fundamental theorem of calculus shows that differentiation and integration are essentially inverse operations, and it allows us to use the techniques of algebra and geometry to solve problems involving calculus. The theorem was discovered and proved by several mathematicians in the 17th and 18th centuries, such as James Gregory, Isaac Barrow, Isaac Newton, Gottfried Wilhelm Leibniz, and Leonhard Euler. An example of the fundamental theorem of calculus in action. Suppose you want to find the area under the curve of the function f, x equals x2 plus sin x, from x equals 0 to x equals 2. According to the fundamental theorem of calculus, part 2, you can do this by finding an antiderivative of f, x, and evaluating it at the endpoints of the interval. One possible antiderivative of f, x, is f, x, equals 1/3 x3 cos x, as shown in one of the results 1. Then, the area under the curve is given by 0 to f, x, dx equals f, 2, f, 0, equals 1/3 2, 3, cos 2, 1/3 0, 3, cos 0, 1.92. This means that the area under the curve of f, x, from x equals 0 to x equals 2 is approximately 1.92 square units. Calculus, a branch of mathematics, has a wide range of applications across various fields. It's used to analyze and understand changing quantities and relationships between variables. Here are some detailed applications. Physics. Calculus helps describe motion, forces, energy, and other physical phenomena. For instance, it's used to model the trajectory of objects under the influence of gravity, analyze electrical circuits, and study fluid dynamics. Engineering. Engineers use calculus to design and analyze structures, optimize processes, and develop new technologies. Calculus is crucial in areas like civil engineering for analyzing stress and strain in materials, and in chemical engineering for modeling reaction rates. Economics. Calculus is used in economics to analyze supply and demand curves, optimize production, and study consumer behavior. It's employed in calculating marginal utility, cost functions, and profit maximization. Biology. Calculus plays a role in modeling biological systems, such as population growth, enzyme reactions, and neural networks. It's used to understand the rates of change in biological processes. Medicine. Medical professionals use calculus for various applications, like analyzing the spread of diseases, modeling drug dosage and interactions, and understanding the rates of change in physiological processes. Computer science. Calculus is essential in computer graphics for rendering images and animations, in cryptography for developing secure algorithms, and in machine learning for training models and optimizing algorithms. Statistics. Calculus is foundational for statistics, helping to calculate probabilities, estimate parameters, and analyze data trends. It's used in fields like econometrics, epidemiology, and social sciences. Finance. Calculus is used to derive formulas for pricing options, managing risk, and modeling financial derivatives. It's crucial in quantitative finance for portfolio optimization and risk management. Astronomy. Calculus aids in predicting celestial events, modeling planetary orbits, and analyzing the behavior of cosmic objects. Environmental science. Calculus is used to model the spread of pollutants, predict ecological changes, and understand the dynamics of ecosystems. Artificial intelligence. Calculus is a fundamental tool in training neural networks and developing algorithms for machine learning and deep learning tasks. Architecture. Architects use calculus to design buildings that can withstand external forces, optimize structural integrity, and ensure safety. These are just a few examples of how calculus is deeply ingrained in various disciplines, aiding in understanding, modeling, optimizing, and predicting real-world phenomena. Its ability to describe and analyze rates of change makes it an invaluable tool for advancing knowledge and technology in numerous fields. Examples of how calculus is deeply ingrained in various disciplines, aiding in understanding, modeling, optimizing, and predicting real-world phenomena. Its ability to describe and analyze rates of change makes it an invaluable tool for advancing knowledge and technology in numerous fields. User explains in detail who had been the contributors to the calculation caged. Calculus has a rich history of contributions from various mathematicians over several centuries. Here are some of the key contributors. Isaac Newton, 1643 to 1727. Along with Gottfried Wilhelm Leibniz, Newton is credited with independently developing calculus. He formulated the fundamental principles of calculus, including the concept of derivatives to describe rates of change and integrals to calculate areas and accumulation. Gottfried Wilhelm Leibniz, 1646 to 1716. Leibniz also independently developed calculus and introduced the notation we use today, such as dx for differentials and the integral symbol. He emphasized the importance of the product rule and quotient rule for differentiation. Leonhard Euler, 1707 to 1783. Euler contributed to the development of calculus by expanding its applications to various fields. He introduced the notation for the derivative f'(x) and made significant contributions to the study of differential equations. Joseph Louis Lagrange, 1736 to 1813. Lagrange introduced the concept of the derivative as a limit, provided a rigorous foundation for calculus, and worked on the theory of functions. Pierre-Simon Laplace, 1749 to 1827. Laplace extended calculus to probability theory and celestial mechanics. His work on differential equations and their applications greatly influenced science and engineering. Augustin Louis Cauchy, 1789 to 1857. Cauchy played a crucial role in making calculus more rigorous. He introduced the concept of limits and rigorously defined continuity, which became foundational in modern analysis. Bernhard Riemann, 1826 to 1866. Riemann's work laid the foundation for a deeper understanding of integration and differentiation. His development of Riemann integrals paved the way for the modern concept of integration. Carl Weierstrass, 1815 to 1897. Weierstrass introduced the concept of uniform convergence and helped establish a solid basis for real analyses, addressing the challenges of rigor in calculus. Henri Lebesgue, 1875 to 1941. Lebesgue introduced the concept of Lebesgue integration, a powerful way to generalize the Riemann integral and address more complex functions and sets. Srinivasa Ramanujan, 1887 to 1920. Although largely self-taught, Ramanujan made remarkable contributions to mathematical analyses, including series and integrals, which continue to influence modern mathematics. Paul Airds, 1913 to 1996. Airds made significant contributions to various areas of mathematics, including calculus and its applications, and collaborated with numerous mathematicians worldwide. These mathematicians, among others, have collectively shaped the development of calculus and its applications over the centuries. Their insights and contributions have not only advanced mathematics, but have also paved the way for the diverse applications of calculus in science, engineering, and other fields. That was it. Bye.